Hey guys, welcome back to the channel. So in today's video, we will be talking about basically buffer solutions, acids and base titrations, and also the Henderson-Hasselbalch equation. So as you guys can see what I've written here, this is the Henderson-Hasselbalch equation, where you've got pH is equal to pKa plus log of the concentration of conjugate base over the concentration of conjugate of acid. So it's a conjugate base over acid, right? And so this is basically what a buffer solution is. So buffer solution is set up when a weak acid and its conjugate base is added together into a mixture, or a weak base and conjugate acid added together. So it's either one of the two, as long as you have the word weak in it. And this is because you'll have a buffer region in the titration curve where if you add small amount of acids and bases to the buffer solution, the pH will not change, and that's how buffer solutions are made. So as you guys can see here on this graph, I've got a weak base and a weak acid. So initially I have 25 centiliters cubed of weak acid, and then I'll be adding weak base. So for simplicity's sake, the concentration of both will be the same, and I'm just adding different amount of acids and bases to each one. So we'll start off with 25 centimeters cubed of the weak acid, and the pH will be at around, let's say 4 to 5, and you've got this buffer region here where the concentration of the acid is the same as concentration of base, and also pH is equal to pKa of this region, because as you guys can see here, there's same concentration of conjugate base and acid. Therefore, log conjugate base of acid will be 1, log 1. And log 1 is 0. So pH is equal to pKa plus 0. So pH will be equal to pKa. And the equivalence point is when the same number of moles of acids and same number of moles of base. Right, so initial number of moles of acid in the beaker or in whatever container you have, and then you add the same exact number of moles of the weak base into it as well to form the buffer solution. And this buffer solution, so at this point, the equivalence point, complete neutralization has occurred, and it's around pH of 7. So move on to this right here is weak base and strong acid together. So weak base, we will start off at around, say, 8 to 9 pH, whereas as you add more acid, you also have the buffer region, but the equivalence point will be at a lower pH, because at this moment here, the pH is dependent on the number of H plus ion released into the solution, because of an acid being a strong acid and the base being a weak base. Alright. And this is what it would look like. And this is the buffer titration curve of a strong base, strong acid. So let's say you start from here. Here, however, we do not have a buffer region because it's a strong base and a strong acid. So this will be at 7, same thing. For strong base, weak acid, we do have it. Let's start from here. Right, this pH over here, be at a much higher one, let's say 10. We do have buffer region. There we go. So those are the buffer regions we do have for the titration curves. And let's talk about Nernst equation. So for Nernst equation, we do know that this is E cell is equal to E naught cell. This is a preview of next lesson. Minus RT over NF log Q. Now, sorry, I think it's natural log LNQ. This is what it looked like. And log basically shows that Q is when the reaction quotient. So it's the concentration of products over concentration of reactants, right? So for example, if I have 3, let's say N2 plus H2, I get NH3. This is in equilibrium. Let's put 2 here, 2 here, and 3 here. Oh, I'm assuming this is right. Oh, sorry. Yeah. There you go. N2 plus 3H2 is equal to 2NH3. So Q would be product, so NH3, concentration of NH3 squared over concentration of N2 times concentration of H2 cubed. This is Q. K is also the same thing, but K is when all of these concentrations are at equilibrium. Right. So this is the only difference between Q and K. They have the same equation. They only take concentration of gases into account, not solid or liquid. And basically, the only Q is reaction quotient and K is an equilibrium constant. And Q can happen at any concentration, but K is when the concentration of NH3 is in equilibrium, concentration of N2 and concentration of H2 is in equilibrium. So those are the ones in equilibrium right here. And as Q approaches K, so if Q is less than K, right, not enough products is being formed. Because if Q is less than K, there's less product, less concentration of products, and more concentration of reactants. And if Q is larger than K, too much products is being formed. So you want to convert the products into reactants or reactants to products if your Q is less than K. So this is the equilibrium constant and equilibrium quotient. And also we'll talk about the fact that we've got Gibbs free energy as well. So basically, Gibbs free energy, you have a lot of different equations, but delta RG, delta R stands for Gibbs energy change of the reaction overall, is equal to negative NF E naught cell. There we go. E naught cell is the standard cell potential. F is Faraday's constant, and is number of mole of electrons. Number of moles of electrons here. Delta RG is also equal to delta H, RH minus T, delta RS. There we go. Also know that delta RG is also equal, because we've got this one right here, it's equal to plus, let's say, delta G naught plus RT Ln reaction constant K. This is at equilibrium, by the way. Oh, sorry, the LNQ is the general equation, but at equilibrium, delta RG at equilibrium will be equal to 0 because of this diagram over here. So imagine this. This is your reactants. This is your products. This is, sorry, free energy. Go. Products. Reactants. This is equilibrium, as you can see here. And so as you go as Q. As you go from reactants to equilibrium, right here, this free energy here. The difference between the level of the reactants and the products will be delta Rg. Here we go. But at equilibrium though, delta Rg will be 0. Because there's no net, it's not spontaneous, but it's not non-spontaneous either. So it's like in between. So rate of forward is equal to rate of reverse reaction. So therefore delta G is equal to minus RT ln K. There we go. T is temperature, R is gas constant, K is equilibrium constant, and this is delta G, give free energy. And you can also learn that the fact that we'll also talk about amino acids, and basically you've got the side chains, and you've got the N terminus, the amino terminus, and the carboxylate terminus. So, as you know, that if pH is larger than pKa or pH is less than pKa, it's going to be protonated. This would be deprotonated. Protonated means that the COO minus be COH, and the NH2 will be NH3 plus. And this is for this too. And here COO8, this is COO minus, plus goes NH2. Generally, this is what we're dealing with for amino acids over here. Right. So this is basically previews of tomorrow's videos, and we also talked about today's videos as well for acids and bases, titration, and buffer solutions, Henderson-Hasselbalch equation, Nernst equation, it gives free energy, this free energy diagram over here. And yeah, I'll see you guys in the next video.